Good afternoon. It is my honor to be here to share our research with you. The topic of my presentation today is BERT-based ensemble model for the statute law retrieval and legal information entailment. Our team consists of 3 members. Xuanlei Shao is a social scientist, and Yi Jiachen is a student of data science, and finally, Sichun Huang, myself, is a legal scholar. I'm in charge of Laboratory of Legal Analytics at National Taiwan University. Therefore, the team name that we participated in this year, COLIEE, is called LLNTU. Through this QR code, you can access to our research. We've trained law students to use technology in information science to analyze legal text, mainly court cases, and we acquire useful insights for lawyers and legal studies. Our team is very interdisciplinary, and this year is the first time we participated in COLIEE Competition. This is a famous international information retrieval competition, had its 7th run in 2020. 4 tasks were included in this competition. Task 1 and 2 were the case law competition, and Task 3 and 4 were statute law competition. We attended only Task 3 and 4. Task 3 is to consider a yes-no legal question queue and retrieve relevant articles from a database of Japanese civil code. And Task 4 is to confirm entailment of a yes-no answer from the retrieved civil code article. The COLIEE organizer provided legal questions drawn from Japanese bar exams and all Japanese civil law articles in both Japanese and English translation. It contains firm relationships between questions and the articles relevant to answering the questions. One point to mention is that our team only processed Japanese data, not including English one. Here is an example of the given data. The T2 part is the bar exam question query, and the T1 part is the article of Japanese civil code relevant to the query. The above is an example where the query ID H18-1-2 is confirmed to be answerable from the article 566, which is relevant to Task 3. And then the pair labeled Y in this example means the answer for this query is yes, which is entailed from the relevant articles relevant to Task 4. For Task 3 and 4, the training data will be the same. In Task 3, the input is a bar exam, yes-no question, and then the output should be the relevant civil law article. In Task 4, the input is also a bar exam yes-no question. And then after retrieving relevant articles using in our method, we determine the output yes or no. The goal of Task 4 is to construct yes-no question answering system for legal questions by entailment from the relevant articles. Before we started, we've done some survey on previous work adopted by the team last year. For example, they use information retrieval engine such as Elasticsearch, Terrier, Indri, Gensim, and etc. Based on the previous work, we think that the most challenging part of the COLIEE are two questions. Number one, how to proceed information retrieval well, and number two, how to ensure models' robustness. We think that the number of given queries is 696, which is quite limited to do information entailment. So we decided to enhance our data not from an external source, but to do it internally. In the beginning, we had 696 bar exam questions as T2 and 767 civil code articles as T1. Our design is to do data augmentation, which is to input the combinations of bar exam question query and article of the Japan Civil Code as continuous strings. That is to say, T2 is combined with every article of the Civil Code, producing 767 samples, which is the number of articles in the Part 1 to 3 of the Japan Civil Code. Among these, only the sample containing the relevant article is labeled as 1, and other samples containing the non-relevant articles are labeled as 0. For example, as Table 1 in our paper shows, the query ID H18-1-2 is deemed relevant to Article 566, so we labeled it as 1. The next page indicates how we proceeded data augmentation. The queries on the left side is exactly the same as the previous page. However, the article here, number 1 and 2, are thought to be non-relevant to the query. So we labeled them as 0 here, meaning that these are wrong pair. These fictitious wrong pair were created by us, not provided by the organizer. As you've seen, in the beginning, we had only 696 samples. But after combining each query with all articles, we construct a dataset composed of more than 500,000 samples, the 696 questions times 767 articles. Next, we allocate the samples in the earlier 11 years to the training set, which has 430,000 samples. And then the samples in the year before the latest year as a validation set, which contains 44,000 samples. And finally, samples in the latest year as a test set containing 53,000 samples. Because the positive samples, which are samples with label 1, are very few, about 1 out of 700, and therefore the data set is imbalanced. We simply upsample positive ones in the training set to be 100 times. This process can be seen as a kind of data augmentation. After data processing, we transform the pairing task to be a binary classification task. We use the BERT for sequence classification. Specifically speaking, we put questions, queries, and articles as a combination, as a continuous string. And then finally, a sigmoid layer is put in the model finally, so that the outcome will become a possibility of the relevancy. The next challenge that we face is how to ensure or enhance the model's robustness. We use above-mentioned samples as inputs, then adopt 3 BERT models to train them. The first one is BERT-based one, which abbreviated BERT JPCWWM. We preserve only the first 384 words, max length 384, which is sufficient to give a good performance, as shown in the figure 1 in our paper. The second BERT model is BERT JPCWWM max length 512, and then the third one is LBERT JP with max length 512. We use Adam as optimizer with learning rate 4E5. This model can indicate how much T1 and T2 are relevant. We train each model independently as usual. Next, each validation sample or test sample is fed into these 3 models, yielding values between 0 and 1. Finally, in the Ensemble layer, these 3 values are averaged to provide the final prediction value. We used validation set and test set to prove that Ensemble BERT model performs better than a single BERT model. What we did is to confirm F2 score performance of each model. The orange line here is the performance of LBERT model, and then the blue line shows the F2 performance of Ensemble model. As you see here, the blue line performs apparently better than the orange line. The next step is to decide the appropriate threshold number. We tested different numbers for the threshold, ranging from 0.2 to 0.99. The record, the F2 score performance of the validation set and the test set of each threshold to confirm model sensitivity. The validation set curve, which is blue one, reaches a peak at the threshold of 0.7. Meanwhile, the test set curve, the orange one, enters into a plateau period at the threshold ranging from 0.75 to 0.82. In order to acquire a stable result, an average curve, the green one, of the validation set and the test set is created, displaying that 0.8 is a relatively reliable and rational decision of the threshold. With the threshold of 0.8, it may be possible that more than one articles are recognized as relevant at the same time. On the other hand, it also happens that no article has the F2 score value greater than 0.8. In this case, we obtain the maximum index to be the most possible relevant article using the arguments of the maximum function. The organizer of this competition also encouraged our participants to submit a rank list with 100 candidates for each query as the long answer. which gave us more opportunities to hit the target correctly. The R5 value here means the recall by using top 5 ranked documents as returned documents, and R10 for our top 10, and then R30 for top 30, which are listed in this table. In terms of performance, as the table indicates, the F2 score of our model is 6587. The precision is also around 68. And then the recall is around 66. It is a stable one. In addition, with the wider rank list, we can provide around 80% of the correct answers in the top 5 trial and over 90% in the top 30 hits. And as a result, the performance of our team ranked number 1 in task 3. And in terms of task 4, we used the same approach to solve task 4. However, compared to sufficient samples in task 3, in task 4, we have only 568 samples to work with. Our model accuracy is 61, which has 69 correct answers for all 112 questions, and it is ranked around the 6th in whole teams. The baseline here is 59 yes among all 112 questions. Well, still our team performs better than baseline a little. So it's the final glimpse at our performance in this competition, and we were very excited and feel satisfactory in participating in this competitive competition. Although our model seemed performed not bad in the competition, it also gave some wrong shots, and then we attempted to find out the possible reasons. Our guess is that perhaps it's the problem of the extraction-based question answering. The model's failing answers can be categorized into 2 types. The first one, when there does not exist any common word for the correct T1 and the respective query T2, our model has difficulties to recognize their relevancy and then points the wrong answer. This kind of mistake happens because the model cannot find sufficient hints to make a good decision. It needs additional information to derive the associations required to identify words belonging to similar concepts, such as legal domain knowledge. Another incorrect answer pattern occurs when there exist several common words for the T2 and T1 pair, so that it easily catches the model's attention. And it seems that our model was not thorough enough when making this decision, and then fell into the trap like a careless student. Well, the above-mentioned 2 patterns of errors in our model indicate that approaches using BERT may solve a certain kind of extraction-based question answering problem, but perform weaker when abstract legal concepts and reasoning are necessary. Finally, we would like to submit some feedback to the challenge questions that we submitted in the earlier stage. The first one is how to proceed IR well. We restricted given data to a data set which contains all possible combination of queries and articles to be continuous strings as our samples. And in this way, the difficult pairing task has been turned to a simpler classification task. And then the samples for training become sufficient in number. And the second challenge is how to ensure models' robustness. The answer or the feedback that we would like to submit is that it's possible to improve the robustness by using Ensemble model rather than a single model. Finally, I would like to express my sincere gratitude to the organizer of COLIEE. It really teaches us a very good lesson. And then if you have any further questions or any opportunities of collaboration, welcome to contact me at NTU. And this is the website of our laboratory. You are more than welcome to visit here. And I'm very happy to be here in Taiwan to welcome you. It's Sichuan Huang from NTU. Thank you.